Is there a right-hand rule for statistics at all?
Yeah, 90% of people are right-handed.
Well, other than that.
There's actually a very close tie between linear algebra and sample theory.
Okay.
And so I can fully see some sort of a connection there. I don't know what it might be right at this moment. Okay. Well, how are we doing?
Good.
All right.
Good job. Let's continue on a little bit. We've got a little bit more time. I'd like to push the envelope a little bit. Okay? And so, right? Let x be a discrete random variable. Do a little bit of new material. And so, back to section 2.1. Back to section 2.1. In particular, discrete random variables. Remember that x is discrete if the possible values of x is either finite or countable. Okay. We talked about that last class, and so let x be a discrete random variable with a probability mass function, and I'll go little p of x of an input. Okay. Remember that for a discrete random variable, the probabilities have to be non-negative and they must sum to 1 across all your possibilities. Right? Remember for p of x, right? We need two things conforming to our axioms, that px of x is non-negative for all x. Right? Don't forget that this x, being discrete, only has positive probabilities on at most a countable number of values. So there's an uncountable number of values for which it would be 0, right? And 2, the probabilities always do for all x that your random variable x can take on must always add up to 1. Okay. We also defined a cumulative probability function, okay, as we're going to use a capital F, and we'll subscript it by our random variable's name, okay? And this, by definition, is the probability that that random variable is less than or equal to that specific value. Okay? By the way, I should relate this to a probability for a discrete random variable, and where px of x is the probability your random variable takes on that specific value. Okay? And I will tell you that on Wednesday's midterm, I said it would cover the material that we've talked about in section 2.1. Well, this is really about the extent of it, okay? Okay? Now, I've done a couple tricky things in the past, okay? Just so you know. Sometimes I give us a random variable x with the probability distribution. Sometimes instead I give the cumulative, right? Right? Suppose my random variable x can take on values 1, 2, 3, 4, okay, and I have something like Okay. Question for you. That second row on here, I have not yet given it a label. Could it be a probability distribution? Could those be P of x's, or could they be cumulatives, capital F of x? Which could that be?
Cumulative.
Cumulative? What argument are you using?
Well, the fact that one of our probabilities are certain by its terms if we were to consider it to be a probability function. But that wouldn't be possible in regards to our other variables, so therefore we have to consider that it might be a cumulative function.
Yeah, for that to be a probability function, one, all the entries would have to be non-negative, but what do they have to do?
Sum to 1.
Which do they? Probably not. Probably not, right? Right? So could that be a cumulative function? It could. It could. Okay. So here is your cumulative function. Right? Find the probability that x, whoops, that's not what I meant to do. Find, I need a pen that writes too, by the way. Find the probability that 1 is strictly less than x is strictly less than 4. Can I tease that out of there? Can I tease that out of there?
I believe you can.
I,
Otherwise, I don't think you'd have asked.
Right. Don't forget, cumulatives are by definition the probability of being less than or equal to that particular value. Right? And we know that this particular value can only take on, if you look at this, I've got a 1, 2, 3, or a 4 with probability 0.4, 0.3, 0.2, and 0.1, right? We want, actually, I'm giving that away. Shoot. That was going to be my question for you. Where did that come from? How can I create that, right? Well, isn't this the probability that x is strictly less than 4 minus the probability that x is less than or equal to 1? You like that sentence right there? Right?
You're going up to 4, and then you're chopping off the bit that's 1 and under.
There you go. Do you see how that's working? Right now. One of those is a cumulative function and the other is not. Which one is?
Less than or equal to 1 is cumulative.
less than or equal to 1 is cumulative, but this one is not, right? Right? But this random variable is taking on these values 1, 2, 3, or 4, right? If it's strictly less than 4, then is it less than or equal to something you can identify?
Yeah.
Yeah? What?
Because, well, if the cutoff is at 4, then
Is-
that means it's
3 and under.
3 and under.
3 and under, right, right.
And that
So-
is cumulative.
So that's the probability x is less than or equal to 3, right? Minus the probability x is less than or equal to 1, or 0.9 minus 0.4, or 0.5, right? Right? Can I create this table? X can take on values 1, 2, 3, or 4. Can I find the probability distribution? Can I find the probability distribution? Well, as a key here, right, the probability px of something, how about if we choose the 2, for instance, is the probability that x is less than or equal to 2 minus the probability that x is strictly less than 2. Are you in agreement on that sentence? Right? Again, one of those is a CDF, but the other one is not. Right? This one here is, this one is not. Right? And so, but that's the probability x is less than or equal to 2 minus the probability x is less than or equal to 1. Do you like that? Right? So do you agree then that that's the cumulative at 2 minus the cumulative at 1? Do you see that if you take the difference of cumulatives at two adjacent values, then you get the probability of just one of them?
Mhm.
Does that make sense? Right? Or in other words, 0.9 minus 0.7 or 0.0, wait a second, let's do this right. 0.7 minus 0.4, is 0.3. Sorry about my sloppy handwriting all of a sudden, right? Do you agree with that argument right there? Right? And so what are these other probabilities? What's the probability that x is equal to 1? 0.4. 0.4. Convince yourself. What's the probability x is equal to 3? Right? Probability of being less than or equal to 3 minus the probability of being less than or equal to 2 would give you the probability x is equal to 3, right? Or 0.2, right? Last but not least, 0.1. Now, is this a valid probability distribution?
Yeah, that adds up to 10.
It adds up.
Or to 1.
There you go. Yeah, the other one. Yes.
The one.
How's that feel for us? Does that seem okay? Yes.
So the first distribution we can tell is not a valid,
It's not a probability
it's not a
distribution.
probability distribution because it doesn't add up to 1.
Exactly right.
However, using the properties of cumulative probability functions, we can turn it into a valid
There
probability.
you go.
Okay.
There you go. Okay. Does that help? Does that feel okay for us? Okay. So now you see, I didn't mean to give the punchline away, but now do you see that this probability distribution does look like that? Okay. Good. So So, by the way, some questions similar to this you might well see in 2 days. Okay? Okay? Let's push the envelope a little bit more.
So we could get this on the midterm.
Something like that. Yes, yes, yes. You know? And in particular, wanting to use that cumulative. Okay. Now, okay? So, I've got, let's get ready. I did that first part mainly because I know you've got a midterm coming up, but let's take this, okay? So let's let x be a discrete random variable with the probability mass function, and I'll give it to you. We just saw it there. X, px of x, taking on values 1, 2, 3, or 4 with probabilities 0.4, 0.3, 0.2, and 0.1. Okay? Okay? And we just saw in that picture that you could sketch that probability distribution. Don't forget that the probability has spikes on the values 0, 1, 2, and 3. I mean 1, 2, 3, and 4, and is 0 everywhere else. 1, 2, 3, and 4 with a height of 0.4, 0.3, 0.2, and 0.1. Okay? Okay? So if we randomly picked a value from this random variable, how much more likely is it that we'll observe a 1 than a 4?
4 times as likely.
4 times as likely. Yeah, yeah. Now, and so, where would you say this now? So don't forget, if we generate a random value of this distribution, right? In fact, roughly what percent of the time would you generate a 1?
Or 40% of the time.
40%, 2 you generate 30%, so forth and so on, right? Right? So what would you call the center of this distribution?
Where or?
Yeah, where?
Oh. Around the 2.
Round 2.
But-
Round 2. Okay. So that kind of brings us to this notion of central tendency. Okay. And you know, I like that around 2. I don't know. We'll figure it out. We'll figure out at least some sense of an answer there at some point, right? Right? We probably don't want to equally weight these 1, 2, 3, and 4. It's not like a 4-sided dice, you know. You know, where they're all equally likely. Now that dice is weighted, so if they were equally likely, then you'd say on average it would be centered around 2.5, but probably not, because the weights are centered on the lower side of there. And so let's bring up a notion called the mean. The mean. Okay, the mean is denoted by the Greek letter mu. Okay, and that Greek letter mu is reserved when you have a distribution. Okay. By the way, before things are done, we don't have class. We got tests on Wednesday. So next Monday, this is going to be known, also known as the expected value of x. I rather like the expression expected value for something you haven't yet observed, you know? And so, yeah.
Oh, before we get too much further, going back to the other page we did with the 0.4, 0.7, 0.9, and 1.0, that works out nicely because they are in ascending order. Will we ever see it? Because if the probability at 2 is less than the probability at 1, you're going to get a negative for that.
Then it's not valid.
Okay.
Right? Because that would produce a negative probability.
Okay.
Right? If you did see something like that, and so by the way, Does a cumulative function have to be increasing?
Yes.
Has to be increasing, right? Right? Because you're always adding probability as you go, right? Right? Good, good. Okay, okay. So, the mean. Here's an equation for the mean. And don't forget, we're talking about where's the center of something that is not symmetric. Okay? There might be different interpretations of what we call the center, right? Right? For instance, the mean is but one calculation. Another calculation might be a median, right? Right? And so the mean is defined as the sum across all x that it can take on of x times its probabilities. Okay? And for this particular problem, that's simply, let's see, 1 times 0.4 plus 2 times 0.3 plus 3 times 0.2 plus 4 times 0.1 with this perfect symmetry we got going on here. What does that turn out to be? Does that turn out to be 2.0? 2? By the way, as a general rule of thumb, the mean, which is neither a person nor a thing, it's its own entity, take some decimal places out on that. So by the way, your estimate of right at 2 is pretty spot on. Okay? The mean is a measure of central tendency. Okay? Another thing that the mean is the mean, if I think about probabilities as weights, right? So here's what I'm doing is I'm taking a weight of 0.4 and placing it on top of 1. I'm taking a weight of 0.3 and placing it on top of 2. So forth and so on, right? Right? Where is the center of mass of that? Right? In other words, you know, like our famous teeter-totter. If I were to take a fulcrum and slide it under here, where would it find balance? At the 2, at the mean. Okay? Okay? Right? Right? And indeed, the mean mu is the fulcrum point or the center of balance. Balance, right? In fact, we can use this example right here. Well, no, we don't need to use that example. Okay, good. And in fact, let's see. Okay. Let x be a discrete random variable with probability mass function piece of x. Okay, right. Then the mean, mu is the sum across all x, okay, of x times its weight. Okay? Now, right? And so, by the way, for a particular distribution, is the mean a constant or a variable?
It's a constant.
It's a constant. Okay. So The center of mass, the center of mass. What does the center of mass even really mean? What is the sum across all x of x minus its mean times the weight of x, right? By the way, an x value minus its mean is known as a deviation. Right? So for instance, because 1 is below the mean, its deviation is going to be negative. Because 2 is right at the mean in this example, that would have a deviation of 0 because it doesn't deviate from the mean, right? So forth and so on. So it's signed a distance from that center point. Okay? And so, let's see, what does this thing turn out to? I remember on homework 1, I gave us a bunch of practice using summation notation. Welcome, welcome. And so, first thing, what can I do to simplify that? Let's see. What do you want me to do first? How about I distribute that probability through, right? Isn't that, tell me if you like this, the sum across all x of x times its probability, right, minus the mean times its probability. Is that a fair statement? Okay. Now can I separate that into two summations?
You should be able to.
Should be able to, right? Isn't that the sum across all x of x times its probability minus the sum across all x of mu times its probability? You agree with that? Agree with that?
And are we also ensuring the fact that we know that mu is a constant and therefore could technically be let outside of the
So we tackled that a second ago. So we all agree that for a particular distribution, the mean must be a constant, right? Right? So fantastic suggestion. A suggestion was, well, if this is a summation and that mu is just a constant, it can be factored to the front. We in agreement there? Right? Let's do that. Right? By the way, this little sketch we're doing right now is foreshadowing some of the things we'll do in the near future. So I like that. If mu is a constant, it can come to the front. Okay, fantastic. Okay. Now you guys have been awesome. Usually this is where I say this is the class participation spot, right? What is this summation that I've got written on the left?
That's isn't that the definition of the mean?
Isn't that the definition of the mean? Awesome. So this is the definition of the mean. Okay.
So mu minus
Next
mu.
question. This summation right here, right? What is that? What's the problem? What's this? The probability of x summed across all the possible values of x.
It's one.
Just one.
Isn't it just 1?
So then it's 0.
Right? You agree with that? We've got a valid probability distribution. The sum across all the possibilities sum to 1. So, in other words, what does this yield?
0.
0.
There's no deviation
Is,
ever.
no, that doesn't
Oh,
say that at all.
no, it doesn't.
That does not say that at all. What does it say? Isn't that what we think of when we say the center of mass? Right? Right? That the deviations on the left-hand side cancel out with the deviations on the right-hand side. Right? Right? Does that make sense? Okay. And so, that's interesting about the mean. The mean is the center of the mass. It's that place where the deviations on the left cancel out with the deviations on the right. Right? Where, most importantly in there, what are we using for weights? We're using the actual probabilities as the weights, because 1 happens 4 times more likely than 4, so it gets weighted 4 times heavier, right? Right? Okay. And so I like doing that little piece right there because it really does show, well, I don't know if it shows, feels to me a very compelling argument for what we mean when we say something is the center of mass. And, oh my goodness, time. Anyways, next Wednesday is our midterm. When we come back next Monday, it's going to be a big class, and we're going to be talking about these ideas here and moving forward. We talked here about the mean as being kind of a measure of where the center is, right? Next question for us might be, how much variation is there within a distribution, right? Right? We would think those deviations would be a fine place to start, but we realize if we just take the deviations, they all cancel each other out. So we're going to have to come up with a different strategy. Okay? Okay, did we do it?
We did it.
Okay, what you got?
Oh, so just, as for what we just did, we should take the cumulative probability stuff, and might be on the midterm. The mean
Will not be on this midterm.
Okay.
Yes, and you can thank the ice storm, because it most definitely typically would be. Okay? All right. Have a fantastic couple days, and I hope this goes well for everybody.
I think I'd actually prefer to have had
Tomorrow at
all of our
11
4
o'clock.
days and have you
Yes.
be on the midterm.
Yes, yeah, right?
Yeah, because now we have everything else.
I got to